Hello everyone, welcome to the live interactive session for the first week of the course Introductory Field Structural Geology offered by NPTEL. My name is Rajiv Mukherjee and I am a Prime Minister's Research Fellow at the Experimental Rock Deformation Laboratory of the Department of Earth Sciences, IIT Kanpur. I will be hosting these live sessions for the coming 3 weeks or the coming 4 weeks, as the course is a 4-week course. So each and every week we will be having these live interactive sessions. So where we will be so in these live interactive sessions, we will be basically discussing about some conceptual problems and some multiple choice questions that are relevant to this course and also for overall understanding of structural geology. So the course, that is the Introductory Field Structural Geology offered by NPTEL, has some specific objectives. So the first objective is to provide a general overview of the subject and develop the basic concepts. And the second is to build up the skills for geometric interpretation and linking the geographical disposition of geological structures that we observe in the field. That is essentially the skills for carrying out lithostructural mapping. Third one is to actually develop a strong sense of scale dependence of geological processes, both in time and space. So that is to interpret the sequence of deformation events that we see in the field. And in the field, we generally see a finite the results of a finite deformation where multiple phases might be overprinted because of multiple phases of deformation in different time. And then we actually interpolate the sequence of events from consecutively measuring the structural elements or the structural attributes. And we also take help from other processes or other subjects like petrography, which is one of the most important aspects of carrying out field geology, metamorphic petrology. Even in advanced stages, we also carry out geochronology. That means we conduct age determination from different minerals. So overall, field geology is a combination of primarily the lithology and its structural disposition. And if you carry out field work in sedimentary basins, then knowing about the provenance of the sediments and the sedimentary structures those will be helpful for determining the age of Yonging direction, the Yonging direction, and sequentially the overprinting relationship between different phases of deformation. So then it comes to develop an understanding of deformation processes and mechanisms that govern the formation of geological structures and their identification, interpretation in the field. That means you may see some lineations or foliations in some exposures in the field or the outcrops. But then your task as a field geologist will be to interpret the large scale structures based on the bits of pieces information that you gather from each and every exposure in the field, and eventually you carry out the lithostructural mapping to interpret whether there is a fold or a fault or any kind of discontinuity within the region that you are studying. And these will actually help us to connect structural geology with the other domains in earth sciences such as petrology, geophysics, hydrogeology, ore geology, mining engineering, etc. And finally, to provide an understanding of lithostructural mapping from outcrop to regional scale that are important for mining and exploration industries. So field geology in particular has a very high demand in areas of mining and petroleum exploration. because these are something that till date cannot be done by AI, because as we know that nowadays everything has got changed by the influence of artificial intelligence, but still there is a large section that requires human resource or the knowledge, human knowledge and the first person interpretation in the field itself. And therefore there is a growing demand not only in the sectors for mining but also sustainability development and how it can be linked with structural geology, such as carbon storage and capture, uh, coal bed methane extrapolation, carbon sequestration, these kind of things that are going on to actually diminish the global warming. So in a way, field geology is a diverse subject, and more importantly, it is an interlinked and interdisciplinary subject. If you are a good field geologist, then it is evident that you have a very good grasp uniformly over a many lot of fields, such as um, metamorphic petrology, igneous petrology, structural geology, sedimentology, paleontology, even in hydrogeology and and many other aspects. So this course will offer a brief development in the understanding of the structural aspect and how this can be correlated with the lithology. Uh, that's it. So, and in these live sessions, we will be complementing what you are already learning from the course materials. So these will mostly focus on clearing doubts on the course materials, discussing conceptual and numerical problems on structural geology that will help in solving the weekly course assignments, and also discussing multiple choice based and numerical questions relevant for national level competitive examinations in geological sciences. So the course outline for the first week was introduction to the field structural geology, and then defining the field area, that is the Shingbum Craton and Shingbum Shear Zone, and different locations where the field works were actually carried out. And then comes the brief idea or brief overview of different structural elements that we measure in the field and how these things are geometrically interconnected with each other. And then finally going on to the stereographic projections to actually find out how on a large scale these bits of pieces of exposure that we measure in the field, they are actually correlated with one to another. So this was the first week's lesson or lectures. And to give an information about the live interactive session, so these live sessions will be held weekly at each Saturday, the same time, that is from 7 p.m. to 9 p.m. Today is 26th July of 2025, and these live sessions will also be run synchronously with the course, and the duration will be 4 weeks. And this is the link to join these live discussion sessions. After each course, these videos of the recorded lecture videos will be available on YouTube, and all the study materials will be uploaded in a Google Drive link where each of you can access what we are discussing each of these live sessions. And you can eventually reach out to me if you want to if you want have any other discussions related to other subjects, especially related to field geology, or if you have any problems such as in numerical or MCQ type problems or any kind of understanding, you can reach out to me and other TAs of this course. And also you can email to Professor Shantanu Misra for further details and discussion. So talking about today's live session, so in week 1 we learned about importance of the subject, that is the field geology, different aspects of structural geology, importance of scale of observation, right? Homogeneity and heterogeneity of geological structures, structural elements and attributes measured in the field, interpretation of structural elements through stereographic projections, and learning about geometric disposition of structural attributes. And about today's topic of discussion, we will be mostly having interaction about week 1 course content and answering doubts if any. solving conceptual questions related to week 1 contents, and finally summarizing and concluding today's discussion session. So we will be solving some numerical and conceptual problems. There are few, and there is another 1.5 hours to actually look into these problems that I have collected and designed. So before going into that, I would like to ask if anyone who have joined this live session. So if you have any doubt regarding the first week's lecture contents, feel free to ask. I will try to answer my capacity, and after that we can go straight into the problem solving session. Okay, so I will now start today's discussion session by solving some problems. So this is a first question. So I have gathered around 14 questions that I will be discussing today, which are relevant for the week 1's content. So the first question is, which of the following options is correct? Number 1, a rock that is homogeneous at outcrop scale will always deform homogeneously at that scale. A rock that is heterogeneous at outcrop scale. Option B, a rock that is heterogeneous at outcrop scale will always deform heterogeneously at that scale. Option C, a rock that is isotropic at outcrop scale will neither deform homogeneously or heterogeneously. And option D, the rock at outcrop scale can deform either or both homogeneously and heterogeneously. So this is a question that is essentially talking about a material's compositional heterogeneity or homogeneity, the scale of observation, and then the mode of deformation. So there are three aspects of the question. So if I may write, what are the three aspects? Number 1 says composition of the sample. Number 2 is the scale of observation. And number 3 is obviously the mode of deformation. So one request to everyone, as you know that I am sharing my screen, so I cannot actually see anybody of whoever have joined this lecture session or discussion session. So if you have any question, just unmute yourself, or if you have any doubt, just unmute yourself, and please feel free to ask, because I cannot see if you are typing any messages over the Google Meet platform, because I am sharing my screen, so I am not available to watch that or to see that. But other than that, if you have any sort of problem in your connectivity, if you cannot hear me, if you cannot see the what am I writing, if any problem or any issues, please feel free to unmute yourself and ask. Okay, so this is a sincere request from my end. Okay, so there are three aspects of this question. One talks about the homogeneity or heterogeneity of the sample itself, that is the composition. Number 2 is the scale of observation, and number 3 is the mode of deformation. Okay, so think for a minute, and if you have any answer, you can always unmute yourself and say what will be the answer. Okay, and there are no marking scheme or anything like that. It is not an assignment, it is just a discussion session. So if you deliver a wrong answer, that is perfectly okay. No one is going to judge you, and feel free to ask. So even having a wrong answer should also encourage others to start a discussion. Okay, so okay, I'm just pausing for a minute and let you think. And please, I want an answer from anyone. So think about the problem and see what comes out. Any answer? Okay, so one thing for sure, we can rule out option C. This is definitely the wrong answer, right? Because neither deform homogeneously or heterogeneously doesn't mean anything. If it deforms, then eventually it will be a homogeneous deformation or a heterogeneous deformation. So this statement itself contradicts the purpose of deformation. So therefore option C is null and void. It will not be a valid option, right? So remaining three are a bit tricky, but if you figure out, the thing is that it is very easy to answer. I mean, it doesn't require any extra knowledge, but just guessing by the common sense, you can actually approach to the answer. Okay, so if I clarify a bit more, homogeneous deformation.
Answer is D, sir. Answer is D.
Yeah, absolutely. Answer D is correct. You're right. So the rock at outcrop scale can deform either or both homogeneously and heterogeneously. So homogeneous deformation, it simply means how the stress is applied on the rock, right? So suppose a material is like this, and you are compressing it from each side. Now, if these are sigma 1, sigma 2, sigma 3, sigma 4, I'm just hypothetically writing, these are the stresses from all the directions acting on the sample, right? So if sigma 1, sigma 2, sigma 3, sigma 4 all are equal, then eventually the material will be shrinked like this, right? But it will maintain the shape and size. Maintain the shape, not the size, sorry. Maintain the shape, and eventually this kind of deformation is known as coaxial deformation. So any deviation from the coaxial deformation is a heterogeneous deformation. Can give rise to heterogeneity. Right? Say for example, development of shear zone. Or planar and linear fabrics. Anything, right? So in that sense, option A will also be discarded, because the mode of deformation doesn't actually depend on the compositional heterogeneity or homogeneity of the material. That is simply not possible, because the mode of deformation is actually controlled by the tectonic stresses, right? The far field stresses that generates from some sort of tectonic activity, right? In a regional scale, any deformation can be linked with the tectonic activity surrounding that region, right? So any involvement of a tectonic activity will somehow give rise to some sort of heterogeneity in the deformation. So if a material even appears homogeneous at outcrop scale, that will not be possible to actually deform the material homogeneously at that scale, right? Even in a homogeneous sample, you can develop some planar and linear fabrics. That simply means that the deformation is not homogeneous, rather it is heterogeneous, because the deformation is not coaxial, and it has some other components like shearing or traction parallel to the surface of the rock, right? So this is another approach through which we are eliminating option A. Now talking about option B, a rock that is heterogeneous at outcrop scale will always deform heterogeneously at the same scale. That is also an invalid option. Say for example, I have a rock that is layered. There are some layerings, right? So even if there is some layerings, if I apply stresses in such a way that the shape of the material does not change, then the size will simply reduce, but eventually the structures within the material will be preserved. It is even possible because now what I am doing, instead of keeping the stresses constant, I am changing these stresses around the material or around the rock each and every time, so that eventually at a final stage there will be no change in the shape or the geometry of the rock or the material. It is possible to achieve just by varying the stresses at each moment of time, and so that the strain that is being accumulated within the material stays homogeneous over all the body of the material, right, within the volume. So if I can do that, then obviously I could actually, in theory, I could preserve the structure as it was before the deformation, right? So that says not necessarily if you have compositional heterogeneity we will always develop heterogeneous deformation. So in that sense, option B also discarded, and that makes that brings us with the only option that is valid, and that also makes sense that a rock at outcrop scale can deform either or both homogeneously and heterogeneously, just because there are certain deviations from the coaxial mode of deformation that can give rise to the heterogeneity. These are called local phases of deformation. That means in a local scale, if you observe a fold, that doesn't mean I mean, if you observe very tight isoclinal folds in a field for a certain exposure, that doesn't mean that the regional fold is will also be going to be tight isoclinal. It is a possibility, but it is not the only possibility. It is possible that the regional scale fold is a large open fold, but in a particular outcrop, in a particular section that you're observing, you can actually get a very tight isoclinal fold or even an overturned fold or very asymmetric folds, whatever, right? So that is possible. So deformation can be independent of the material that you are studying. Okay, thank you for the right answer. uh, let's move on to the next question. Okay, this is something you should know. So there are 4 geological events which are number 1, subduction of an oceanic crust; number 2, fissure volcanism at Hawaii; number 3, mantle convection cycle; number 4, deformation during impact cratering. Arrange the above mentioned events in the increasing order of their time scale. So shortest duration to longest duration. Is uh, that is the question. Any guess from anyone?
Probably D, sir. 4, 3, 2, 1.
So 4 is deformation during impact cratering. 3 is mantle convection, 2 is fissure volcanism at Hawaii, and 1 is subduction of an oceanic crust. Okay. You guessed it almost right, except for one sequence. I think that,
Can I guess again?
yeah, sure. Any multiple times. There is no
C option 4213.
4213. Yeah. So 4 is impact cratering, 2 is fissure volcanism, 1 is subduction. Yeah, correct. Option C is the right answer. What is your name?
My name is Brijesh.
Oh, okay. Congratulations. Thank you, Brijesh. You guessed it right exactly. So option C is the correct answer, because impact cratering, the time frame that we talk about is just uh, less than a second. So that's how fast the deformation takes place. So within a thousand of fractions of a second, the impact occurs, and that's how the elastic energy is emitted through shock waves, and that instantaneously transforms each and every material that we see around. And yeah, it's a very fascinating kind of deformation externally imposed on the Earth's surface, and the temperature reaches well above mm, 2000 to 3000 degrees centigrade of temperature, and it generates a deviatoric stress that is impossible to achieve anything inside the earth more than 30 to 40 GPa, gigapascals of pressure, huge pressure and huge temperature within just a fraction of second. And all the quartz that we see, they get transformed instantaneously to coincide a high pressure temperature phase, and that stays in that level or in that phase, because all of the elastic energy is being emitted so fast due to the rise in temperature and pressure. Yeah, so that takes less than a second. Then comes fissure volcanism or fissure eruption. So it starts from days to years, right? So fissure eruption takes starts from the fracturing of the earth, and the lava comes out and it flows, and there can be different kinds of flow rate based on the viscosity of the magma, right? So if you have a basaltic magma, the viscosity will be less because of the lesser silica content, and it will flow very rapidly. It can be seen within days that all the areas are being flooded, and there are some casualties because of this extreme lava flow, wildfires. All these kind of natural hazards can take place within a day because of volcanic eruptions from fissure eruption from basaltic lava. And if the lava is slightly rhyolitic, or there is a little bit of excess silica present within this magma, or then the lava flow can be a little sluggish, and then it can continue over the years, right? So in Hawaii, actually, small scale intermittent eruption takes place every day, and incrementally they pile up over the previously deposited lava, and they actually form these intertrappean structures, and it continues over years and years, and until you can see that okay, something has grown out of the fissure. And so does this spreading happen. So there is a range of this process, so it can start from the days, and it easily can continue up to 10 to 15 years and so, right? And then comes obviously subduction. Subduction is a process from start to finish. It easily takes more than 10 to 15 million years, right? So the time scale of a subduction of an oceanic lithosphere is around 180 million years. You should know that the the youngest oceanic crust that we see in the mid-oceanic ridges are just days or 2 years old, and then as we go farthest away from these mid-oceanic ridges, we calculate the temperature of the ocean floor lava and the basaltic rocks that comprise these oceanic crusts, and we also figure out their ages through marine magnetic anomaly, and they give us the answer that the oldest you can get to a subduction zone is nearly about 180 to 200 million years old, and that is at par with the Wilson cycle that was proposed by famous geologist Wilson, who proposed that each and every plate has its birth and its demise, and that's how the cycle goes on, and it specifically maintains a rate of 180 million years from the present day tectonic configuration because of the gradual cooling of the earth. Now the thing is that if you went back some 1,000 million years ago in the Proterozoic, you probably would have found that the subduction process, if at all it was uh, comparable with what we see today, that would have taken more or less than 10 million years or so. So over the years, the heat has been dissipated from the earth and it is gradually cooling, and so does the viscosity of these all plates are increasing, the rigidity of the plates are increasing, the plates are becoming stiffer and stiffer by the day, and that is why the process itself goes on slow, because of because heat is the main driving energy for all these processes, and since the heat is being dissipated out of the planet, these processes are becoming slower and slower. Now subduction is a process that is directly controlled by the mantle convection inside the earth's lower mantle, right, and even in some part of the upper mantle, right. So the lower mantle convection starts from the core mantle boundary and gets all the way up to the upper mantle, and that is probably the largest distance any liquid covers within the earth, that is in the order of 2,000 kilometers abruptly. A 2,000-kilometer long journey from the core mantle boundary to the Earth's upper mantle, and this takes easily more than 500 to 600 million years. That's how these convections are occurring, right? So mantle convection. So from the core mantle boundary to the upper mantle, it can easily take this much amount of time based on several factors, such as the viscosity of the magma, not the magma, just viscosity of the lower mantle rocks, the geothermal gradient, and also the heat dissipation rate. So there are also many other thermomechanical parameters that actually govern these cycles, but on a broader aspect, we can say that these are the primary factors that govern the rate at which the convection cycle goes on, and it easily takes this much amount of year, and that's how the convections operate. Now there are several discrepancies, and there were several, not discrepancies, there are several school of thoughts that suggest that there are multiple layers of convection, right? So 2-layer convection model, multiple layer convection model, and unified layer convection model. So these are all geodynamic theories that currently is uh, in the geoscience community that people talk about and carry out research. But the main thing is that whether there is small scale convections or large scale convection doesn't matter, because it easily over surpasses each of the processes that we actually can infer from the surface of the earth, and also some deeper part through drilling projects and so on. So our knowledge from the direct evidence is mostly related to the fast 100 kilometers of the crust and the mantle, right? But beyond that, whatever there might be, we rely on uh, the geophysical data, the seismic data, and the thermal conductivity and so on. So these are some indirect methods which allows us to interpret the internal structure. But we don't know for sure. There can be a multiple approaches or hypotheses for answering the most intriguing questions that still persist in the earth science subject. Okay, third question. Following are the hand specimen images of bayonet iron formation and migmatic gneiss. So the first one is a sedimentary rock. The second one is a metamorphic rock, right? Then says choose the correct option, and it is given that A and B both are heterogeneous in microscopic and macroscopic scale. That means if you have dendron formation and gneiss, if you take them in your hand, that is in hand specimen scale, and then you prepare thin section from the samples that spans over some microns or so, then it says they will appear heterogeneous even if you observe through the microscope or you are seeing on the hand specimen. Second option is that A is homogeneous in microscopic scale, B is heterogeneous in microscopic scale. That means if you prepare thin section and slides, observe them through microscope, you will see that banded iron formation rock is BIF is actually homogeneous, or and the gneiss is heterogeneous. Option C, A and B are isotropic in macroscopic scale but anisotropic in microscopic scale. Isotropic means the properties or compositions, they are direction dependent or not. Anisotropic means that there is a direction dependence of the composition or the property. If certain properties are X and Y, then if we go along one direction and find X, and if we go to another direction, if we find Y, then we suggest that X and Y are equal if that is isotropic, and X and Y are not equal if the sample is anisotropic. So that is how option C is defined. And option D is that A and both are anisotropic in macroscopic scale but heterogeneous in microscopic scale. Okay, so what will be the answer? Yeah, so since I am sharing my screen, I actually cannot see who is raising hand or typing any message. So it is, I guess, better to actually unmute yourself and speak out.
B,
Sorry, I could not hear you.
B option.
B option. And what is your name?
Pawan.
Okay, thank you, Pawan. Yes, you're correct. Option B will be right. You see, because we are making thin sections, it is hardly, I mean, if this is, say, 5 centimeters or even this much amount of in length, and
నాకు ఆ రెండు
for making thin sections, we will just need less than a millimeter space. So we can cut samples out from here, here, even from here. But these are layered structures, right? But if you prepare thin sections from these locations, you will find that there is a homogeneity in composition. But gneiss actually is comprised of many lot of things. There can be biotite and quartz and feldspar, right? And then you can have some plagioclase, and these kind of things will be mixed together, right? There can also be some mafic minerals, right? Like amphibole or like that, pyroxene, anything. So even if you prepare thin sections from locations like here and here and here or here, you will see deformed structures. Deformed structures and heterogeneous composition. So gneiss is such a rock where the deformation penetrates even into the micron scale, and that is why when you are making thin sections out of gneisses instead of having banded iron formation, so you will see that there are signatures of deformation that makes it heterogeneous at the microscopic scale. And since BIF, when we are talking about just BIF, we are referring to undeformed banded iron formation. If it is deformed, then we say it as meta BIF, right? That means there is a metamorphism taken place within this material, and because of that metamorphism, there is certain deformation accommodated within the material, and eventually it will become heterogeneous even in the microscopic scale. So since it is not that case, anything that has certain deformation like gneiss, it is intensely deformed and foliated. That means that if you prepare thin sections, you will also find signatures of deformation within each and every mineral grain. They will show some alignment or orientation. Those are known as the shape preferred orientation and crystal preferred orientations, like that. And this is how even from thin section you can actually interpret how much strain has been accommodated within this pigmented gneiss because of the deformation, right? So one thing is intriguing. Apart from contact metamorphism or metasomatism, which are a very special kinds of changes and alterations that take place in the rock, if we generally refer to regional metamorphism, so for a regional metamorphism, there has to be, whatever insignificant that may be, but there has to be some sort of deformation within the rock as it undergoes some chemical or compositional changes. So if you ever encounter some metamorphic rock, be sure that if it is a regional metamorphism, there has to be some uh, deformation within the material. You may or may not find deformation in a single outcrop, but if you search long enough for the region you are studying, you will always end up having some outcrop where intense deformation or localization has taken place. Because deformation in nature, by definition or by virtue, it always becomes heterogeneous. It does not stay homogeneous. It cannot be, because it is not a theory, and in nature we see that deformations are always heterogeneous. And heterogeneity in deformation means that you will not get same signatures of deformation in each and every outcrop. There are some features that will be present in certain outcrops, and if you go to another outcrop, you will not find them. And that is why the field locations in this course of introductory field structural geology is impressive and unique, because each of these field locations, they not only show incremental stages of deformation, but they also preserve the previous one. That means from outcrop 1 to outcrop 2, if you go from places to place, you will find newer signatures of deformation as well as previous signatures. And that is why it is a very good example for studying overprinting structural relationship. That is why Shingbum shear zone is very much special. You probably would have learned about the 3 quartzite bands that we have studied in the field. Now, the importance of these quartzite bands are that they preserve all sets of deformation in each of these locations. Some quartzite band should show you just one phase of deformation, and then you go to the next place, you will find not only the second phase but the previous phase, or the phase 1 of deformation, is also stored. Then you go to the next location, you find that along with the first and second phase of deformation, there are overprinting relationship from the third generation of deformation. So increasingly the structures become complex and complex and complex. And then finally we arrive at a location very special, because it is an exposure of nearly about 20 to 30 meter long, and there we will see intense structural deformation within intercalated layers of metasedimentary rocks, and all the phases of deformation that eventually we will be mapping throughout this course. You will find that all these phases of deformation are clubbed together within that single location, and that location is extremely deformed with multiple phases of deformation. So I have carried out several fieldworks in my academic tenure, and I have never seen such beautiful exposures other than the Shingbum shear zone, because of this preservation of deformation. But if there are heterogeneity in deformation, you would end up having undeformed rocks all over the place, but then suddenly you will find an exposure where extreme strain localization has happened, and eventually you will get a shear zone. And that is how the regional metamorphism can be correlated with extreme heterogeneous deformation, and also the changes in the chemical composition of the rock. Okay, so moving on to the question number 4. Which one of the following options is correct? So brittle deformation followed by ductile deformation, overall structure is continuous. Brittle deformation followed by ductile deformation, overall structure is discontinuous. Option C, ductile deformation followed by brittle deformation, overall structure is discontinuous. And option D, ductile deformation followed by brittle deformation, overall structure is continuous. So I'm sure you have some sense of brittle deformation and ductile deformation. So you don't have to know much about all the processes of these kinds of deformation. You will eventually learn from the coming weeks. But even if you understand what does brittle deformation mean and what does ductile deformation mean, you can easily answer the question. And talking about continuity and discontinuity, it is just simply, if you mark one of the layers and try to figure out whether there are any break in the trail or of the layer, then it is discontinuous. And if you find that, okay, so I am getting all the layers one by one in sequence and there is no break within that layer, within those layers, then eventually that is continuous. That is what continuity and discontinuity means in this question.
Option C.
Option C, ductile deformation followed by brittle deformation. Overall structure is discontinuous. Yeah, overall structure is surely discontinuous because, so if you follow the red lines that I am drawing, this is a dike, right? And these layers, they are folds, right? So there is a fold and there is a dike. So have you ever heard of a cross-cutting relationship? It says that if a feature, if a structure A cross-cuts another structure B, and makes structure B discontinuous, while it remains, while A remains continuous, then A is younger than B. Okay. So easily you can see that this dike has intruded within the fold because the dike is continuous. Within the dike there is no discontinuity. But it is generating discontinuity within the fold because you can see the layers are slightly shifted because of this intrusion of the dike, and that is why it is discontinuous. So obviously intrusion of the dike is making the fold discontinuous while the dike itself remains continuous within the structure. So dike is obviously younger than the fold. Now which one of these is ductile deformation and which is brittle deformation?
Fold is ductile and this dike one is brittle.
Obviously. So since the fold is a ductile deformation, that means it is uh, obviously younger, obviously older, and then the brittle deformation. Okay. So then the dike is younger means it will be followed by the fold, right? So yes, option C is correct because ductile deformation followed by brittle deformation, because ductile deformation takes place earlier and then it is followed by the brittle deformation, that is the intrusion of the dike, and that makes the overall structure discontinuous, because when we are talking about the overall continuity of these layers, we see that there is a little shift, they are not continuous. So the cross-cutting relationship helps us interpret the relative ages of the structures or the layers that we see in the field, and this kind of fracturing that takes place that makes the intrusion of dike or quartz or veins like so, these are essentially late stage deformation phenomena in a regional deformation or metamorphism, and these are helpful for interpreting the relative edges of exposure to exposure, and so we can actually make the stratigraphy. Okay, so cross-cutting relationship is very important for establishing the stratigraphy of a region. Okay, so moving on to the next question. GPS stations are installed at various locations and elevations along the entire length of the Himalaya to track the rate of upliftment of the mountain and the motion of the Indian plate. So what kind of structural analyses are involved in the process? Geometric analysis, geometric, kinematic and mechanical analysis, geometric and kinematic analysis, and option B, numerical analysis. Right? So let me just give you the premise. Geometric analysis, that means observing the geometry, right? So you go to a field, you see structures, right? So the purpose of carrying out field was limited to small scale exposures until we had satellites. Now we can carry out field works within a range of thousands of kilometers just by an hour through satellite imagery and remote sensing. So this is, in a sense, this is also a field work that we are doing currently from the live data of the satellites that are giving us information thousands of kilometers above the mean sea level, and literally they are in the boundary between the outer space and the Earth's atmosphere, right? So from that perspective, we can only get the relative motions of the GPS trackers, right? Because we cannot actually see how the plates are moving, right? Because they are very slow. But we get information about the relative movements of each and every GPS, their location, and how fast they are moving like this. So so if this is the belt of Himalaya, and this is the Indian plate, and this is the Eurasian plate, so there are GPS installed all over the Himalayan range, and we can measure how fast they are moving and in which direction they are moving. So obviously from these data we can actually interpret how Indian plate is still undergoing deformation and making the Himalayan orogeny much taller and taller by each year, right? So this is the study of an active deformation which is currently going on in each and every second. We measured the data from the GPS trackers. Now there are two important aspects. One is the velocity of the GPS trackers, and number two is the direction of movement of each GPS stations, right? So velocity is important because it gives us the kinematic analysis. Kinematics means the study of the rate of any process, and that can be linked with the dynamic processes such as the stress and the strain and so on. So kinematics or the kinematic analysis is involved through judging the rate of the motion of each of these GPS stations or GPS tracker. So this involves kinematic analysis. Now the direction of movement obviously is related to the geometry of the Himalayan fold belt, right? So in a sense that the GPS trackers that are installed all over the range of Himalaya They are currently giving us live information about the geometry and the kinematics together, and that helps us interpreting how Himalaya is still growing and why it is still the youngest mountain belt in the world, right? So this gives us the answer that option C will be correct in this case, because geometric and kinematic analysis are performed to actually infer the process of the mountain making that is currently going on in the Himalayas. Okay, so let us move on to the next question. This is a simple one. How igneous petrology and structural geology are linked in understanding the volcanic topography and geomorphology? Option A, by knowing the composition of the lava, its viscosity and rheology. By knowing the eruptive style and composition of the lava only. By knowing the deformation behavior and eruptive style only. And none of the above. We just discussed this phenomena earlier, right? In another question about the fissure eruption. So I guess you can guess what will be the right answer.
I think option C.
By knowing the deformation behavior and eruptive style only. Yeah, deformation behavior and eruptive style, but then eruptive style it is dependent on the composition, right? That means fissure eruption mostly takes place for basaltic lavas, and uh, what is that thing is called stratovolcano, right? Stratovolcano or dynamic eruption, right? That takes place generally for felsic lavas or rhyolitic lava. So then the eruptive style can be related to the composition. That means it is the petrology of the lava, right? And then once we know the petrology of the lava that I was talking about previously, so petrology will directly say us, okay, so how the viscosity will change, right? Because if the lava has higher silica content, it will have higher viscosity, right? So it will flow sluggishly compared to a lava which has lesser silica content, lesser free silica content, and that is some basaltic lava. So felsic lava will have higher viscosity and higher water content. It will erupt. It will be explosive volcanism, right? Whereas for basaltic lava, the water content is very much less, and so does the silica content, and that is why its viscosity will be much lesser compared to a rhyolitic lava or felsic lava, and it will generally try to flow rapidly or smoothly over the surface without making any cone shaped volcanic eruption, right? So that is why understanding the viscosity and obviously if you know the viscosity of the material, you should be able to know how it will deform. Very high viscous material means it is stiffer and it will obviously produce much strong solidified material compared to a rock which has lesser viscosity, and it will eventually try to flow, and there will be some weakness within the material which has high capacity to flow, and it will eventually form bubbles, right? So in that case, structural geology is also related to the rheology. That means how the deformation is taking place. So it is also important to know the eruptive style. It is also important to know the composition because it is linked with the eruptive style, and it indirectly gives us the information about the viscosity and the rheology. So correct answer would be not just option C but also option A. So this can be these two can be both viable options for this question, right? Because we need to know the composition of the lava. That's how the petrology will be linked, and by knowing the composition of the lava we can say its viscosity and rheology, and just by looking into the structures in the field we can say about the deformation behavior from the different volcanic structures, and obviously the geomorphology will be giving us the eruptive style, right? So eruptive style means whether it will be fissure or dynamic or volcano eruption. That means it is developing a cone or a dome, whatever these kind of things may be. So together, option A and option C both are valid because it encompasses the all aspects of the answer we are looking for. Okay, now let us go to question number 7. In which of the litho units would you expect to see a nice folded structure in outcrop scale? Option A granite, option B basalt, option C intercalated shale limestone, and option D quartzite.
Um, Option C.
Exactly, intercalated shale limestone. Because folding, the general model of folding requires competency contrast. So if there is a material A and there is a material B, the relative ratio, or the relative not the relative ratio, the relative strength between the layers A and B will govern the localization of deformation. right? So if the strength of A is equal to strength of B, even if you try to deform these material, you will end up having some fractures at most and some like that. There will be no such thing as ductile deformation. But if strength of A is higher than strength of B, if you compress this, right, then there will be, and that means not just higher, it can also be lower. The thing is, if the strength of material A is not equal to strength of the material B, in the easiest way to say that, that means there is a difference between the strength of the material at the interface, and that thing is known as the competency contrast. So if there is a competency contrast, if you compress the material, then you will tend to have been developing buckle folds. So any kind of ductile deformation structure requires some heterogeneity. Now this heterogeneity comes from the compositional heterogeneity within the material. In a same material, that means it is compositionally homogeneous, it is rather impossible to localize the strain or the deformation into some particular region without having any compositional heterogeneity. Even if you keep on changing the stress at every point of time in the material, it is very hard to develop continuous ductile deformation localized within some regions of the material that is virtually homogeneous at every scale. That is why developing a fold, nice folded structure within granite, basalt or quartzite is difficult, because all of these things are compositionally homogeneous. So to localize the deformation, that is to make a fault or to create a nice folded structure or even a shear zone within the material, you need some heterogeneity at some point, however the minute quantity that might be. Even in some microscopic amount, if there are some heterogeneity or nucleus of heterogeneity that will start to nucleate the localization within the material, and eventually it will start, even eventually it will continue up to the largest scale of structure that you are observing. But for that you need some compositional heterogeneity. So to develop these kind of folded structures and ductile signatures like shear zones or like that, you will need some heterogeneity in terms of the composition, so that there will be a variation in the strength of the material. Now that is important because you need materials which have different strength. You can obviously have different compositions of material, but eventually if those two materials end up having the same strength, then all of the same, there is no point of having ductile deformation in the material. So in terms of compositional heterogeneity, I am specifically talking about heterogeneity in the strength of the material. If there is a heterogeneity in the strength of the material, then only it is possible to localize the deformation due to the ongoing due to the active stresses, and eventually you can generate fold or shear zone like structures. So option C is correct, and that is why all the most beautiful exposures of folds you end up seeing either in gneissic rocks or extremely foliated schist kind of rocks, or these kind of intercalated shale limestones which are soft in, which are soft rocks to fold, and there is some heterogeneity in terms of the strength of the material, and that is how you will end up having nice exposures of fold. Okay, question number 8. So it says that two rock units P and Q are undergoing deformation at a depth of 5 km beneath the continental crust and oceanic crust respectively. Calculate the difference between the confining pressure experienced by Q and P. Consider the densities of continental crust and oceanic crust as 2600 kg per meter cube and 2900 kg per meter cube respectively. So this is continental plate or continental crust, and this is oceanic crust. Which one is thicker, continental crust or oceanic crust? What do you think?
Thicker or say denser?
Thick, denser, density is given, so obviously you know that oceanic crust is much denser than the continental crust. I am talking about the thickness. So the general average thickness of both of the crust, which one is thicker?
Oceanic crust.
Exactly the opposite. So continental crusts are much thicker and oceanic crusts are much thinner. The average thickness of a continental crust is nearly about 35 kilometers, right? Whereas the average thickness of an oceanic crust is only about 5 kilometers. Why so? Because the composition of the continental crust is mostly felsic. So it is made up of quartz and feldspar. These materials are less dense, and that is why in order to maintain the total amount of mass, you need larger volume of the material because the density is low, whereas the density of the oceanic crust is much higher, and so to conserve the mass, right, so you need less thickness to actually maintain the mass balance. And it is important because of the principles of isostasy. So you must have heard about the Airy's and Platt's principles of isostasy, and that is how it is related. It is simply coming from the buoyancy of these crusts which are overlying on the asthenosphere, and their disposition over the surface is controlled by their thickness and their density. So you have two vital informations. The thickness of the continental crust is 35 kilometer and the thickness of the oceanic crust is nearly about 5 kilometers, right? So when we are talking about beneath the continental crust, 5 kilometer beneath the continental crust, then that means the depth below continental crust will be 5 plus 35. Beneath the continental crust means below the continental crust, just at this boundary. No, sorry, 5 kilometer beneath the continental crust. I'm sorry. It will be 5 kilometers in beneath the continental crust means from the top surface you are going 5 kilometers. Sorry. So you are going top surface from the 5 kilometers here, and for oceanic crust top surface, from top surface to the depth of 5 kilometers. Oceanic crust 5 kilometer, right? So at this point, how much pressure will be experienced in terms of the thickness of the material and its density? So we know that pressure can be calculated as the thickness h times the density times the acceleration due to gravity. So h rho g is the pressure, right? So for continental crust, we can calculate the pressure 5,000 meters times 2600 times 9.8, right? This amount of Pascal. And for oceanic crust, the same formula can be applied, and that will be 5,000 times 2900 times 9.8 pascals, right? So can you calculate what this value will be?
The first one is 1274, 5 times 0,
1274.
5 times 0.
Okay. And
The below one is 1421,
hmm?
5 times 0. Not 31, sir, 21.
Okay, so the difference in pressure will obviously be 1421 this much minus Pascal. And now if I try to convert it into megapascal, in terms of megapascal, because we talk in terms of megapascal and kilobars and gigapascals in geological setting, you just have to divide all the thing by 10 to the power 6. So if you just divide by 10 to the power 6 the subtracted value, you can get the difference in the confining pressure generated at these depths for continental.
14.7 megapascal.
14.7 megapascal, right? Okay.
Yes.
So this is the answer. This much amount of pressure difference will be generated 5 kilometers beneath the continental crust and 5 kilometers beneath the oceanic crust. So this tells us that the stress required to, so the indirect implication for this exercise is that to gain an insight, that means, okay, so this pressure what we calculated just, this is a confining pressure. Now an example of confining pressure that is very easy to say. So if I hold a paper in air, right? So for example, I have this copy, and hope that you can see it. So this is the top page, and there is nothing above this top page, right? Now with my right hand here, I will apply a certain force or stress onto this paper, the top paper specifically. Now confining pressure means if I am applying stress from this direction, then certain suppression should also come from the top, which will resist whatever the force I am applying from the side. Now since there is no resistance above these top paper or top page, it is very much easier to fold it, right? Like this. So it is much easier to deform when there is no external confinement, right? But if I try to push at the bottom, so and if I even close the copy, right? So there are a lot of pages above this. So I put my finger here, right here. This was the page that I initially folded when it was the top page. Now I am closing it and I am putting a lot more paper above it. So there is some force simply by the weight of the other papers. We are generating some confining pressure. Now in this case, if I try to fold it, it would require much more larger amount of stress to actually fold the papers. It will not become easier than the first case. So this implies that even at the same depth of 5 kilometers, to deform a continental crust is much easier to deform a oceanic crust, right? Why? Because of the difference in the confining pressure. The strength of the material at higher confinement increases because of the extra resistance provided by the confining media, and that is why you get less amount of deformation signatures 5 kilometers down the oceanic crust than a continental crust. If you go below 5 kilometers in a continental crust, you will see easily strain localization and shear zones, whatever not. So these are possible. So some brittle fractures, joints, large fracture networks generating filled with veins and pegmatites and so on. So these are, so the continental crust is full of lot of complex deformation structures. But if you go down to at the same depth for an oceanic crust, it becomes very hard to find these kind of complex deformation structures if at all these high confining pressures are maintained. So that is why confining pressure is important to understand the deformation condition. If we apply the same differential stress or the deviatoric stress to deform the material, higher confinement would resist the deformation and would what can I say? It will make it a lot stronger than expected, and to get fractures and fracture networks and shear bands, whatever or not, it will become harder and harder to get these kind of brittle deformation signatures at higher confinement. That is why deformation within the oceanic crust is dominated by plastic deformation rather than having ductile brittle deformation or brittle deformation in the crust. So crust essentially has these brittle deformation signatures just because it is incapable of generating that much amount of confining pressure for a given depth. Okay, so move on to the next question. A foliation plane of attitude 045 60 degree contains mineral lineation if the trend of the lineation is 0.75, find the plunge amount of the lineation on the foliation plane. So we will now solve some algebraic problems. So these are not stereo net problems, but rather you can apply some algebraic formula, trigonometric formula to actually calculate pitch, plunge, the deep, apparent deep, strike, trend, bearing, whatever. So these kind of structural attributes will be easier to calculate. So this is the strike angle of the foliation plane. And we generally refer to it as phi. So that is 45 degrees. And then we have trend of the lineation. And that is generally theta, which is 0.75 or 75 degrees. Now we need to calculate the difference between phi and theta, which we can say as theta minus phi is equal to 75 degrees minus 45 degrees, and that is 30 degrees. This is known as the structural bearing of the lineation. And it is commonly termed as beta. Then the question asks the plunge amount of the lineation, which is generally written with small p. So there is a algebraic relation, trigonometric relation, which is tan of plunge amount is essentially equal to the tan of the deep amount of the plane times times sine of the structural bearing. Keep in mind, delta will be the deep of the foliation plane. Okay, so tan p is equal to tan 60 degree, right, times sine 30 degree. So sine 30 is half times tan 60 degree, and then we can calculate p simply by having the tan inverse of this entire value, that is 0.5 to times tan 60 degree. So if I just calculate, so can you calculate these value of tan inverse 0.5 into 1.732 and get me the answer of the angle? So is anybody calculating? Okay, so the answer is 41 degrees. So since the trend of the lineation is 0.75, so we can say that the plunge of the lineation is 41 degrees towards 0.75. So this will be the answer. Okay. So let us jump into another problem like this. So foliation plane of attitude 040 45 degree contains a mineral lineation. Now instead of having the trend and the plunge, we are asking if the pitch of the lineation is 30 degree, then find the trend of the lineation on the foliation plane. So given information just like before, okay, so in the previous slide you should remember these trigonometric formula. These are very helpful for competitive examinations because these kind of questions are frequently available, frequently occurring in all the geoscience examinations currently in our India, and they ask these kind of basic questions. If you have remembered this formula for calculating the pitch, plunge, deep strike, etc., you can get the full marks. So another set of formula that I am showing you, in this case, if you have the known value of pitch, the strike, the deep, and and these kind of things, then you can easily infer the trend of the lineation and in fact the plunge. So we will use this formula. So the given information is phi, that is been described before, is 040, that means 40 degrees, right? Now pitch angle, let us define it as r, is given as 30 degree. We have the deep angle, of the foliation plane delta, which is 45 degrees, right? And we have the strike, and we have to calculate theta, which is the trend of the lineation, right? So if yeah, so the formula for this kind of problem is that cos of the pitch is equal to the sorry, not cos of the pitch, um, tan of the pitch angle is equal to the tan of the structural bearing divided by cos of the dip, right? Remember, beta is the structural bearing and it is defined as theta minus phi, or whichever is greater. Sometimes phi is greater, then you take the difference between phi and theta, not theta and phi. So this is the interchangeable value, right? So tan r means tan 30 degree. We have to calculate the theta value, but we can calculate tan beta as so tan beta will be tan 30 is how much? So this is tan 30 degree and cos 45 degree, right? So then if you calculate beta, this will be tan inverse tan 30 degree times cos 45 degree, right? And eventually if you calculate that, cos 45, so it's root 2 0.408, and it's near about 22 degrees. So theta minus pi is equal to 22 degree. Then theta is actually 22 plus 40 degree. That means it is nearly about 62 degrees, right? Okay, so this is the trend of the foliation. Sorry, trend of the lineation on that particular foliation. And again, another type of combination that is been given here. So the structural bearing of a lineation is 45 degrees. So structural bearing means we are talking about the beta. So in the previous formula, you should note this relation. It is the pitch, this is bearing, and this is the deep. So this is the trigonometric relation between deep of the foliation plane, pitch of the lineation, and bearing of the lineation. Right? In the earlier formula, this was the plunge, deep, and the bearing. So now in this formula or in this problem, we are given the bearing is 45 degrees, deep of the plane is 35 degrees, plunge of the plane, plunge of the lineation, sorry, on the plane, it is 25 degrees, and to be measured pitch of the lineation. Right. So in this case, the formula is cos of the pitch is equal to the cos of the plunge times cos of the bearing. Therefore, the pitch will be cos inverse cos of P times cos of beta cos P is 25 degrees, bearing is 45 degrees, and we simply have to calculate the cos inverse of this value. And this is nearly 49 degrees, which says that pitch is 49 degree measured towards 49 degree measured toward the 45 degree bearing. Okay, so this is how we could answer. And again, you should focus on this formula. Right, this entails the relation between the pitch, plunge, and the bearing. So make list of the 3 important formulas that I have shown here, and these are the geometric relation between all the structural attributes, the trigonometric relations, and you can easily apply them to calculate these kind of calculate the parameters for these kind of problems. They generally appear as multiple choice questions in national level examinations. Okay, a very easy question. A dipping limestone bed with a true width of 5 meters shows an apparent width of 10 meters on a horizontal surface. Then what is the true depth of the limestone bed calculated in degrees? So this is the horizontal surface, which is 10 meters, but the true thickness of the or the true width of the 5-meter bed is actually calculated as 10 meters on the horizontal surface. So if this is the bed and if this is the true thickness of the bed, right? So because of this angle, so this is 5 meters, it appears as 10 meters on the surface. So we have to calculate this angle, not this one, sorry. So we have to calculate this angle theta, which is the depth of the bed. It is easy that the depth of the bed can be calculated as sine theta which is sine inverse half, that means 30 degrees. So the correct answer will be option C, depth of the bed. Now moving on to another question. Structure contours of a bedding plane at 100-meter intervals are spaced in such a manner that the horizontal equivalent distance is 65 meters. The depth of the bedding plane is to be the four options, which are 33 degree, 47 degree and 87 degrees, right? So in a map you see contour A and contour B. So 100-meter intervals are in the profile section. So if there is contour A here, then contour B is over here, and the vertical distance between them appears, the actual vertical distance between them is actually 100 meters, but in planar view it appears as 65 meters. Right? So the beds must be dipping like this, and that is why if this is contour B and this is contour A, somehow the extrapolated distance is appearing here, which is 65 meters. Right? So this distance, horizontal distance is 65 meters and the vertical distance is actually 100 meters, and this is how the beds are dipping. So this is contour A and this is contour B. We simply have to calculate the angle here. So this is the base of the right angle triangle, this is the this is the perpendicular, and this is the angle theta. So one thing for sure we can do is that we can calculate the tangent here, right? Perpendicular by base. So we can calculate the tangent. Mm, just a second. Sorry. And this ratio is 1.538. So theta will be tan inverse of 1.538. So this gives the value of 57 degrees. So the dip of the bed is 57 degree and the option is C. Correct option is C. So just the last question here, which says that a sandstone bed whose attitude is 09030 is exposed on flat surface, right? So 09030 means the strike is east-west, right? So the strike is east-west. This is north. So if the strike is east-west, then in terms of right-hand rule, it will be dipping towards along the south, right? Can you tell about the right-hand rule? Okay, anyway, let us just focus on the fact that it can dip on both the ways, just for sake of argument. Now let us just focus on the fact that if we apply the right hand rule, then we can find out that the dip can be on the north or the south. Considering in this situation, we say consider that the bed is dipping towards the north, right? So in a stereographic projection, we may find the bed is dipping like this. Okay? So this is the 090 strike line. Okay, so the true thickness of the bed is 100 meters, right? Find the width of the outcrop of the sandstone bed on the ground along north 30° east. So true thickness of the bed along this direction. So if no, sorry, the apparent thickness will be, so if this is the true thickness of the bed, and this is the angle of the dip, and this is the apparent thickness on the surface, right? So along north, say for example, this is the strike line 090. First we need to find what is the apparent thickness along this direction, right? We get this value as 100 meters. So we have to calculate what will be the apparent thickness of the bed which is exposed along the north, right? So the relation will be 100 meters over the apparent thickness. So if this is XYZ, then the YZ line will be basically equal to XY line divided by sine of the bed theta, sine of the deep angle of the bed. Now that is 30 degrees, so we can say that 100 meters divided by sine 30 means it is almost equal to 200 meters. So this is the apparent thickness of the bed along north direction, which is 200 meters, right? Now the question asks, if I am going along this direction, which is 30 degree from north, and if I find a section of the bed along that line which is exposed on the plane or the surface, flat surface, what will be the thickness along that direction? So again, we have to calculate that this is the XY line which we know, sorry, this is the YZ line which we know for certain has a thickness of 200 meters, right? And we have to calculate the thickness, say for example O here, what will be the direction of the apparent thickness, what will the value of the apparent thickness if we go 30 degree from north along the direction of north 30 degree east. So simply we need to calculate the value of OZ. So OZ, YZ by OZ is basically cos 30 degree, right? Then OZ will be actually YZ by cos 30 degree, and that will give us the value to 31 meters approximately. So along the north 30 degree east direction, the apparent thickness of the bed will be nearly around 231 meters if the true thickness is given as 100 meters and the deep of the bed is 30 degree. So with that, I end today's discussion session. It is already past 9. I'm sorry for the delay in this case. But anyway, we had a fruitful session today, and the next live session will be exactly 1 week later in the same day, the same time from 7 a.m. to 7 p.m. to 9 p.m. and hope to see that you guys are joining again, and we will have the discussion session on the week 2 lecture content. So with that, I am closing today's discussion session. Have a
Thank you,
good
sir.
night. Thank you.